Let us resume 9.2. In the previous video, we talked about the estimation theory, the confidence interval, and the sample size. Now let's talk about hypothesis testing. And here is a nice example. The following is the blood type distribution table of the United States based upon a recent study published in 2008. By the way, here's a source if you're interested. Suppose that a random sample of 150 recent donations at a certain blood bank reveals that 78 were type A blood. Does this result suggest that the actual percentage of type A donation of this blood bank is higher than that of the national average listed above? Set up the hypothesis and test them using the significant level of alpha equals to 0.01, 1%. Well, let's see, we have two competing proportions, 78 over 150, and that's gonna be 0.52, 52%. And also from this table, we get 42% actually. We have two type A. Rh positive plus is 35.7%. And Rh negative A is 6.3%. Add them up, we have 42%. Now we have these two competing proportions. Which is the null hypothesis, and after getting that null hypothesis done, we have to draw the normal picture around the null. Now, which is it, 0.52 or 0.42? It'll turn out that 0.42 is the right one. Let's go over some criteria. Null hypothesis is past value. Well, it is coming from 2008 study, or the study conducted even earlier than that. So it's past result. Number two, it should be general population. It's coming from the entire US population here, while the other 0.52 is coming from this particular example, 78 out of 150. So this is specific versus general. Criterion number three, which one is associated to the sample study of sample size of 150? Well, it's this one. 52%, and that should be the specific one, X bar value. So null is the other one. We went through three criteria and all three agreed. 42% is the null and 52% is the observed proportion. Consequently, we end up with this hypothesis setup. Null hypothesis, about 42%. Alternative hypothesis, we observed 52%, so the alternative hypothesis will be greater than 42% or significantly bigger than 42%. By the way, if you want to be really precise, you may want to use this kind of notation because this is proportion. Instead of mu, use pi. But then again, I usually don't like to do this because pi is usually reserved for something else, 3.14, that irrational number. And of course, you can do the same thing here. For proportion, parameter is pi and the proportion is p. But again, p is usually reserved for probability in this course, so I don't really like to do that either. So I'd like to stick to mu and x as we have done before. Consequently, we end up with this standard error computation. Please note that I used the probability for the null hypothesis here, 0.42, not the other one. If we have to find out the confidence interval based upon this sample study, then we have to use 0.52 because we are not considering the table at all. But this is hypothesis testing. We have to use the null hypothesis here. All right. Now that we found out all these, let's draw the picture. And that picture has to be drawn around the null value of 0.42. And where is 0.52? Well, it depends upon the critical value here. If 0.52 is in the red region, too far away from the null, if it is in the blue region, close enough to the null. Now, what is this critical value? Well, we have to set up the same thing. Z-score is n minus center over standard error, and that Z-score has to be associated to this 99% here, this blue part, left-hand side. Well, here we go. N minus center over standard error has to be Z-score associated to 99%. Let's look up. 99% should be the second page. 0.99, yeah, this one over here is coming from about 2.33, approximately 2.33. More precisely speaking, about 2.326. And solving this equation, you're gonna get x is about 0.51, as you see over here. That is the critical value. Consequently, we end up with this kind of picture here. Yes, 0.51 something is the critical value, and 0.52 is bigger than that. Consequently, it's coming from the red region, too far away from the null. Consequence, we reject the null hypothesis and accept the alternative hypothesis. Yes, there is a bias. In this particular blood bank, or the people around this blood bank have more type A blood than national average, maybe a little bit higher concentration of Asian population. We can do the same thing using the probability value approach. Setup is the same. 0.42 is the computation I got for national, and 0.52 is the computation I got for local. The null hypothesis, the real mean population, or real proportion, excuse me, should be 0.42, not too different from there. Alternative hypothesis, well, we observe 0.52, that's bigger. So we think the real proportion is significantly bigger than 0.42. Okay, the same. And standard error computation, the same computation. Square root of p, 1 minus p over n. But for that proportion, we use 0.42, the proportion for the null hypothesis. Punch in your calculator in, you're going to get this value, which we will recycle later on. Initial picture is a little bit different from previous method. We are not looking for the critical value. We simply plot 0.52 and find out the probability of this red area. If it is too small, then we are gonna if it is too small, then that's roughly speaking, the probability that null is right is too small. Consequently, we are going to take alternative hypothesis. If this p-value is sufficiently big, then we are going to accept the null hypothesis. There's a bit of a confusion here because this method is not as intuitively clear as the critical value method, where you can clearly see the distance concept playing a role here. This is a critical value. Is x bar value close enough to the null, or is it too far away? It turned out too far away here. Intuitively clear, but the probability method, on the other hand, is not that clear. So you have to know the meaning of this p. Precisely speaking, it's a conditional probability that we end up with observed proportion 0.52 or bigger, given that the null is right. Or roughly speaking, given that we have this observed proportion of 0.52, the probability that null is right. Not really accurate, but it works out most of the time. Now, how do we calculate that probability of that red region? The same thing. and minus center over SE. So this is 0.52 minus 0.42 over the standard error. Calculate the z-score, we end up with 2.481 approximately speaking, and look up the z-table. 2.48. Where is 2.48? 2.4 and 8. 0.9934 approximately speaking. Excuse me, 0.9934. So you have to subtract 0.9934 from 1. So you're going to get 0.0066, something like that. I'll be more precisely 0.00654. In any case, it's less than 1%. So probability is less than alpha value. So what do we do? Okay, this is just a computation. Yeah, this is just a computation. The probability is less than alpha, so what do we do? What do we do? As a matter of fact, I should have hidden this one. The answer is right here. Okay, we reject the null and accept alternative hypothesis. As a matter of fact, that was a mistake. This should have been hidden so that I asked you that question and about 10 seconds later, I should have shown you this, and that wasn't really necessary. Anyway, okay, here is the conclusion, the final picture. The probability turned out to be about 0.0065 something, less than 1. So what do? We reject the null hypothesis and accept the alternative hypothesis. If you like this probability value method, please go ahead and do that. It looks like our textbook author likes probability value approach a lot. I don't. I'd much prefer to use this classical method because it is far more intuitively clear how the conclusion comes. If x bar is too far away, accept alternative. If x bar is close enough to null, then accept null hypothesis. In this case, too far away because the critical value turned out to be 0.51 something, and 0.52 is even farther away from the null. I like this one a little bit better. In any case, if you do these right, you're going to end up with the same result. Now, you can set up similar kind of problem with this table. For example, let's see, what is 37.4 plus 6.6? Let's see. There should be about 44% of the people. There should be about 44% of O type bloods. Excuse me. The proportion, the national average proportion of O type blood is about 44% according to this table. So we can set up similar type of problem, say, okay, let's recycle the same figure. 78 out of 150 recent blood donation turned out to be O-type blood. Does this result suggest the actual percentage of type O donations of this blood bank is higher than that of the national average listed above? Well, we can do the same thing here, except that this time the null hypothesis should be 44%, not 42%. In the end, you're going to get something like this. Oops. This is 4, okay. And then if I do that, then 0.52 turned out to be close enough to the null, because if you do the same computation with O-type blood, then the critical value turned out to be 0.53 something. You can set up similar type of problems for B-type blood or RH-type blood. You can do various things.